Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 3 for this week. And we're going to be talking about lapse rates today and the two main types that we concern ourselves with in the field of meteorology. One is what we call a dry adiabatic lapse rate, which has to do with the way air parcels behave when they are not saturated, and a moist adiabatic lapse rate when an air parcel is saturated, and how that affects the rate at which it cools as you go up through the atmosphere. So we're going to get into all of that, plus a little bonus topic at the very end, which I hope you'll find interesting. So we need to start off with some definitions, and I need to shrink myself so you can see those definitions. And here we go. So the word adiabatic, and I actually went to the American Meteorological Society glossary to get the best definition of this that I could possibly get. But the word adiabatic means a process in which there is no exchange of heat or mass with the environment. Any change in internal energy is a result of compression, warming, or expansion, cooling. So nobody is actually, holding a flame next to this air parcel and heating it up. It is only changing temperature because it is responding to changes in pressure that it is experiencing as it goes up or down, okay? But no actual heat being added to the system itself. Okay, now a lapse rate is defined, and you probably all know this, is the decrease of an atmospheric variable with height, the variable always being temperature unless otherwise specified. So we talk about a temperature lapse rate. It means the rate at which the temperature decreases as you go up in the atmosphere. Now, the dry adiabatic lapse rate, which is the rate at which air parcels cool when they are not saturated, is about 9.8 degrees Celsius per kilometer, or about 5.4 degrees Fahrenheit per 1,000 feet, okay? Now, the moist adiabatic lapse rate is going to vary according to both temperature and pressure and moisture content, okay? So it can range anywhere from 3.3 degrees Fahrenheit per 1,000 feet to the dry adiabatic lapse rate, which is 5.4. And that typically occurs when you get so high up in the atmosphere and it is so cold and there is so little moisture left that it basically is a dry adiabatic lapse rate at that particular point in time. But the hotter and more humid it is, as you head into the lower levels of the atmosphere, then at least initially it's going to be that lower lapse rate, the 3.3, and then it'll gradually increase as you go up. All right, so here's the famous QT log P diagram that I've showed you before. Do not worry about understanding what all of those lines mean and the numbers and all that sort of stuff. Just a couple of things to keep in mind is that they call it a skewed T-chart because the lines of equal temperature are skewed, okay? So they're oriented like this. The lines that are horizontal like this are lines of equal pressure, and they become increasingly far apart as you go up in the atmosphere because the mass in the atmosphere is not distributed in a linear fashion. It's distributed in what we call a logarithmic fashion. And so all of the mass, not all the mass, but a good bit of the mass is all piled up near the ground where gravity is the strongest. And then gradually, as gravity loses its punch as you go up, then the atmosphere becomes less and less dense with time, okay? A couple of other things here. These very faint orange lines that are oriented like this, these are the dry adiabats. So if an unsaturated air parcel is moving upward, it's going to follow this path. So you can see how the temperature would decrease as it goes up. These lines that are curved in here are called moist adiabats. And the reason that lapse rate is less than the dry adiabatic lapse rate is that once you get saturation, then you start to release what we call latent heat. And so now, because of that saturation process, now you're not going to be cooling as quickly as you did when the parcel was not saturated and that latent heat was not being released. Finally, and I doubt seriously you can see these lines, if these are the lines of equal temperature here, there's a very faint dotted line that isn't quite parallel to this, but almost, okay? It's actually slanted up this way. And those are called mixing ratio lines, and they're basically lines of equal moisture content, okay? So as air rises, the dew point will fall at a certain rate per 1,000 feet, but it doesn't fall nearly as quickly as the temperature does. All right, so with all that in mind, Let's assume we just have a typical summertime day in North Carolina where the temperature is 95 and the dew point is 77, and everybody's taking a deep breath and drowning because it's so humid outside. All right, so 95 degrees is down in here, and so we take that up the dry adiabat, the closest dry adiabat we can find in the diagram, up to about this point here, and then we take the dew point of 77 and we take it up the mixing ratio line. That's that very faint dotted line that you probably can't see. But you take these two lines up their respective lines until they meet, and that is called the lifting condensation level, okay? And that's where the cloud base is going to be if you have a heating-induced convective cloud. So the temperature at that level is about 72, okay? Now, if that air parcel was not saturated and it continued to be unsaturated, it would cool at the dry adiabatic lapse rate, and by the time it got to about, say 35,000 feet, it would have a temperature of 85 degrees below zero, okay, Fahrenheit. However, because it is saturated and it is releasing latent heat, it follows those moist adiabats, and by the time it gets to the same elevation, instead of it being minus 85, it's minus 17, which is a 68-degree difference, all right? And this is what plays a big role in thunderstorms, is that buoyancy is one of the driving forces where the air parcel is buoyant, or it's warmer than its environment, and buoyancy is a force, which means there has to be acceleration, and that air parcel is going to accelerate upward. And the bigger the difference between its temperature and the environment's temperature, the more buoyant it is, the more acceleration you're going to get, and the stronger updraft that you're going to get in that thunderstorm, okay? So a difference of 68 degrees when it gets to this elevation is pretty darn significant. And when you've got a dew point of 77, it is going to have a significant influence. Okay, so beyond that, I thought it might be fun to share with you a little technique as to how you can estimate how high the base of the clouds are. And this only works on a sunny day where the atmosphere is well mixed. And have you ever seen those days where you have a whole bunch of cumulus clouds and the bottoms of them are perfectly flat and they all appear to be at about the same elevation? Well, that's indicative of the fact the atmosphere is very well mixed and you have a dry adiabatic lapse rate below that cloud base, okay? Now, if it's a cold, rainy day, or really any sort of a rainy day at all, this ain't gonna work. It's only gonna work on those specific types of days. So, and I just put that there on line 1, so a little bit of redundancy, okay. So the temperature decreases, and I always use 5.5. Technically it's 5.4, but let's go with 5.5 just for simplistic purposes here. And then the dew point only decreases half a degree per 1,000 feet. So the temperature and the dew point for every 1,000 feet are getting 5 degrees closer, okay? The dew point's going down a half, but the temperature's going down 5.5, and so for each 1,000 feet, they're getting 5 degrees Fahrenheit closer. And so let's assume the temperature is 95 and the dew point is 75. If the temperature dew point spread is 20, then how many thousands of feet must an air parcel rise before it becomes saturated? Well, if they're getting 5 degrees closer every 1,000 feet, you simply divide the spread, 20, by 5, and you get 4, which is going to be in a cloud base of 4,000 feet above ground level. Now, if none of that makes sense, let's do it a little bit of a different way here, okay? So we're going to look at the elevation above the ground, the temperature of an air parcel, the dew point of an air parcel, and then what the cloud base would be once that parcel becomes saturated. So at the surface, we've got a temperature of 95 and a dew point of 75. So obviously the air is not saturated. Those two numbers are not the same. We go up 1,000 feet. The temperature drops 5.5 degrees to 89.5. The dew point drops a half a degree to 74.5. So now the spread is 15 degrees, but again, not saturated. At 2,000 feet, the temperature decreases another 5.5 down to 84, and the dew point goes down a half a degree to 74. So now the spread is 10. At 3,000 feet, take another 5.5 off of 84, get 78.5. The dew point drops another half, 73.5. Now the spread is 5 degrees. And finally, at 4,000 feet, the temperature drops 5.5 from 78.5 to 73. The dew point drops a half from 73.5 to 73. The two are equal. The air parcel becomes saturated and the cloud base is at 4,000 feet. So again, on a well-mixed sunny day, if you see those flat cloud bases and you're sort of curious as to how high that base is, if you can find out what the temperature and the dew point are, you can make a very, very close estimate as to how far off the ground that cloud base actually is. All right, hope you found that at least somewhat interesting. There are the credits, and that is bonus weather video number 3 for this week. Next one coming up on Monday. Now, I am going to have, here's another bit of TMI, all right? I am going to have one of those lovely colonoscopies on Monday morning. So I do not know how sedated I will be Monday afternoon. My past experience is that I really am pretty functional within a couple of hours. So it should not be a big problem, but I just wanted to mention that to you in case something goes awry. But that's on Monday, and that's the next time I'll see you, both for the daily and the bonus. So you all take care, folks. Have a great Friday evening, an even better weekend, and we'll talk to you Monday. See ya.